Hi, I'm Dave Siever of Mind Alive Inc., located in Edmonton, Alberta, Canada. Today, I'm going to talk to you about transcranial DC stimulation. As we can see, transcranial DC stimulation has been around for a long time. Here is Duchenne de Boulogne in 1855, and we have Baron Rockwell in 1871. Transcranial DC stimulation did fall out of favor due to lack of scientific evidence and procedures. However, with the development of modern EEGs and electrostimulators, transcranial DC stimulation re-emerged in the 1950s. Transcranial DC stimulation involves the application of a small electrical stimulus applied to specific sites across the cranium. The electrical stimulus flows across the brain. Transcranial DC stimulation affects pyramidal neurons and likely astrocytes contained within the glia, and they serve to modulate neuronal activity. The anode, or the positive side, enhances cortical function by as much as 20 to 40%, often within 1 hour. The cathode inhibits cortical function, anywhere from 10 to 30%. Here we have a pyramidal neuron. And what we're showing is an anode, or a positive polarity, applied to the skull, which is that yellow curve. And somewhere across the back of the brain or the back of the head, or perhaps a contralateral shoulder, we have the cathode. And this allows the current to flow down through the pyramidal neuron such that the axon has a positive charge. Now typically, all neurons have a negative internal charge relative to the outside membrane of roughly minus 65 volts internal. If we place a negative anode along the end of an axon of a pyramidal neuron, we can reduce its polarized potential by as much as 10 millivolts. This would push the resting potential from 65 millivolts down to 55 millivolts and make the neuron more easy to fire. If we reversed our electrode such that the anode was at the end of the axon, we could further polarize the neuron and make it less likely to fire. This is the premise of transcranial DC stimulation. Some other aspects of transcranial DC stimulation are that it has been shown that the anode reduces GABAergic activity. GABA influences the neurons by slowing them down, whereas glutamate increases neuronal activity. And what we're seeing here is if the anode reduces GABA activity of the neuron, then the neuron will be more excitable. If the cathode reduces glutamergic activity of the neuron will be more relaxed and less excitable. Transcranial DC stimulation has been shown to influence EEG activity. As we can see here, cathodal stimulation, or the negative electrode, increases delta and theta brainwave activity while reducing beta brainwave activity. We can also see that anodal stimulation, or the positive electrode, decreases delta and theta brainwave activity while increasing beta brainwave activity. We can see here, and this fits in nice with the brainwave model, that if we're going to be decreasing delta and theta brainwave activity while increasing beta activity, odds are we'll have an increase in cerebral blood flow. And what we see here is anodal stimulation applied for 7 minutes with a 7-minute break, and then reapplied for 7 minutes with another 7-minute break, and then reapplied again, has a tendency to push an upward trend in cerebral blood flow. We can also see here with cathodal stimulation, applied the same way, 7 minutes on, 7 minutes off, 7 on, 7 off, and 7 on and 7 off, that there is a downward trend in cerebral blood flow. It was also found that when the current was doubled, cerebral blood flow could be increased by 5%. There have been many studies done on transcranial DC stimulation, at least 150. We can see here just general studies on brain function. 15 studies, substance abuse 5, boosting mathematics 2, traumatic brain injury studies 2, Alzheimer's and dementia 4, behavioral studies 8. There are working memory studies, both with Parkinson's and declarative memory. You can see there are quite a few studies done on depression, and probably even more than 10 at this point in time. There's studies on the sensory motor cortex, and there are at least 40 of those. Studies on stroke, studies on tactile perception, on pain, on sensory perception in general, specifically also for auditory perception, for somatosensory perception, for visual cortex and visual perception, and for tactile perception. Other studies include the general physiology involved with transcranial DC stimulation and neurotransmitter effects, effects on EEG, effects on cerebral blood flow, animal studies, efficacy and safety, migraine studies, epilepsy studies, and literature reviews in general. Most research has been done by Nisch and his colleagues at the University of Göttingen in Germany. Other authors, however, include Fregni, Paulus, Entel, Kinsis, Hoffman, Cruz, Pascal Leon. More of these are involved with Harvard College. Most studies use 25 square centimeters, 36 or 49 square centimeter electrodes. They place their reference on the contralateral orbit or shoulder, and most involve strictly the contralateral orbit just above the eye on the opposite side of the brain where the stimulating electrode is. One of the problems with transcranial DC stim research that has gone on over the years is that the studies failed to look at the effects of that reference, which was typically a cathode, over the area of the brain in which it was placed. Nisch and Paulus found that it was much better to have a small active electrode and a large reference electrode. They also determined that 17 microamps was the threshold current for sensory motor results. However, other studies involving depression and cognition found that 40 microamps per square centimeter was indeed a required stimulus threshold in which to have an effect on brain function. Here are some pictures depicting electrode placement. Typically, for more peripheral electrode sites such as frontal, temporal, parietal, occipital, we would use the headband around the head. For sites near the vertex, such as motor strip and cingulate sites, we would typically run the band underneath the chin. Now we can see in this picture here that we have the reference electrode under the ipsilateral or same size shoulder as we have the stimulus electrode. And although that can be done, we have really shown that for the sake of demonstration in these slides. Traditionally, it would be more proper to put your reference electrode on the opposite shoulder of your stimulation electrode. So how do we determine the current under an electrode? In this example, supposing we were stimulating with 1 milliamp, which is very commonly used in transcranial DC stimulation. If we had a 5 centimeter by 5 centimeter electrode, totaling 25 square centimeters, we would simply take 1 milliamp and divide it by 25, which would yield 40 microamps per square centimeter. Now supposing we were using that same electrode but stimulating with 2 milliamps. Well, we would just simply double it and have 80 microamps per square centimeter underneath the electrode. Supposing we were using an electrode that was perhaps 6 by 6 centimeters, totaling 36 square centimeters. Again, we would take the 1 milliamp, divide by 36, and this would yield 27 microamps per square centimeter. The same would apply with a 7 by 7 centimeter electrode, which yields 49 square centimeters in area. Divided into 1 milliamp would give us 20.4 microamps per square centimeter. Now supposing we were using only 1 milliamp, but we wanted perhaps 80 microamps per square centimeter. We could simply take that electrode and just cut it in half. If we had 12.5 centimeters squared rather than 25, we would now get 80 microamps per square centimeter underneath that electrode. Typically, the electrodes are tuned to the current that is stimulated, because most of the research certainly shows that we should have in excess of 40 microamps per square centimeter. What happens if we started stimulating with high numbers, like 100 microamps per square centimeter? The biggest drawback with stimulating with high levels is that it becomes quite uncomfortable and itchy, and sometimes there's a burning sensation under the electrode. So it doesn't make sense to apply a great deal of current, that which is way above what has been proven to be clinically effective. In the case of the electrodes with our Oasis Pro, we use 3.8 times 4.5 centimeters, yielding 17 square centimeters, or we'll say 18 square centimeters under the sponge. At 1 milliamp, that yields 55 microamps per square centimeter. In almost all cases, this is indeed a very effective stimuli. However, some cases of depression have required that people stimulate with higher levels, perhaps using 1.5 milliamps or even 2 milliamps, which would yield 110 microamps per square centimeter. However, this is very rare, and I would never suggest that we would start at such a high current. I'd recommend we start at 1 milliamp, and if we're not getting results fairly quickly, then increase the current. Our reference electrode is 5 by 10.2 square centimeters, yielding 51 square centimeters and probably 52 square centimeters because the sponge spreads it out a little bit. And that yields 19 microamps per square centimeter. And the reference electrode is indeed very comfortable to use on another part of the head or a contralateral shoulder, or even a neck placement in the case of prefrontal or frontal lobe work. Here is an example of a client we had who had severe depression and had attempted suicide twice in the 2 months prior to coming into our office. We can see a couple of things. This is a QEEG of her brainwaves. The 1 to 4 hertz represents delta brainwave activity. The 5 to 7 is theta brainwave activity. 8 to 12 or 13 would be her alpha. This is 14 to 15 or 13 to 15 hertz is relaxed attention, and that's what they call beta 1. Roughly 16 hertz up to 20 or so is considered beta 2 group, which is active attention, and above 20 is considered to be anxious attention. A few things come to light here. We see that she has a lot of alpha activity right here on her prefrontal lobes. This is not a good way to function, as high alpha activity on the prefrontal lobes means that she has impaired ability to resist fear responses. So all kinds of things will trigger her into fear. In this case, much of her fear is triggered by conditions of ego. We can also see that she is slowed, and that exacerbates that problem of being able to extinguish a fear response, but it also adds in the inability to reason well, and which she clearly does not do. We also see that the alpha hotspots in pink are mostly located on the left side. This indicates that she has depression as well. So we have a person who goes into fear easy, doesn't reason well, and has depression, and so she always thinks about what's going to go wrong. Well, if you think on those terms, you're going to be in big trouble. And as a result of that, this hot beta activity all through this zone is representative of extreme anxiety, which she has. It was my objective to try to reason with this girl because she has a great deal of baggage that has resulted from growing up in her life. And so it was my intention to try to speed up that brainwave activity. We can see here in just one session, we've reduced almost all of that 9 hertz activity, and we've sped her up to 10. This makes it easier for me to reason with her when she's having a faster brainwave. We can also see that we are looking at her at roughly 2.6 standard deviations from the norm. 9 sessions later, zoomed in more tightly to 2.5 standard deviations, we can see that The 9 Hertz activity has almost cleared up completely, and her brain is running faster at 10, and the distribution of those alpha hotspots is much more normalized across her brain. In other words, she's less depressed and more reasonable. And the fact that we're zooming in more tightly means her reaction to fear is getting under control. When working with transcranial DC stimulation, I highly recommend that you get a Brodmann area chart. And Brodmann area charts can be found in several locations on the internet. Skilltopo.com has some very good reference material on Brodmann areas. Using Brodmann information, we can do all kinds of interesting work. For instance, it's well known that typically for depression work, it's best to have the anode at the location of F3 and sometimes even the temporal lobe at T3, and putting the cathode on the right-hand shoulder. Sometimes, however, with depression and alcohol cravings and food cravings, we have a hyperactive right frontal lobe, which is location F4, and we can take a similar sized electrode as the anode and put it on F4. And in fact, what we would be doing is we would be enhancing the happy side of the brain and settling down that negative fear side of the brain. For attention, we can alternately place an anode on each prefrontal lobe at FP1, FP2. And 1 week run it here, the next session run it here, and alternate it from session to session. The other possibility is that we could use a larger electrode and double the current, or take a long electrode that's skinny and cut it in half to make a skinny electrode and place it across at the standard 1 milliamp rating. We can also place the cathode on the base of the neck. That way the current would be running through the pyramidal cells, through the brain, and out through the neck. For insightfulness, a study has shown that putting the anode on T4 and the cathode on T3 has boosted insightfulness. Studies have also shown to boost socialization, it helps to increase awareness of social cues such as body language, facial expression, verbal intonation, and so on. And this can be done by placing the anode at different sites along the temporal lobes and right parietal cortex, and using the contralateral left shoulder for the cathode. For math enhancement, it has been shown that by placing the anode over P4, that's the parietal lobe on the right side, and the cathode over P3 has been an effective approach at boosting math skills and math ability. In the case of vision, and in this particular example, contrast discrimination for slightly different shades of color, to enhance that ability, the anode was placed along O1, OZ, and O2, and the cathode was placed along C3 or perhaps CZ or even C4. And you can enhance that part of the brain for contrast discrimination. The cathode at the occipital cortex also impaired contrast discrimination as well, so you can go both ways. In the case of boosting auditory perception, it was shown that, in this example perhaps if you want to sing better in the choir, maybe you're a musician, to enhance pitch discrimination of music, the anode was placed on T3 and the cathode was placed on the right shoulder. In the case of enhancing motor ability and simultaneously reducing pain, it was shown that, for instance, for right side body pain, you could place the anode over C3 and the cathode over FP2, or the prefrontal cortex. For left side body pain, place the anode over C4 and place the contralateral cathode over FP1, and again above the orbit of the left eye. Another method of reducing pain which Mendonca looked at, he thought, well, is really the motor strip the issue with reducing pain? Or might it really be that the prefrontal lobes have the inhibitory circuits for pain? So he tried another approach. He tried stimulating either prefrontal lobe just above the orbits, or basically at FP1, FP2, and he put the cathode at the base of the neck. And he found indeed that by putting the anode on the prefrontal lobes, he was able to reduce the perception of pain. He also reversed this and put the cathodes there as well, and found indeed that the anodes worked better. In my opinion, it's always better to work with anodes because the cathodes could impair attention and socialization ability and reasoning ability. So I would recommend also sticking with the anodes above those orbits and placing the cathode at the base of the neck. I'm Dave Siever of Mind Alive Inc. of Edmonton, Alberta, Canada. Thank you very much for listening to this lecture on transcranial DC stimulation. I hope you found it both interesting and informative. And I'd like to remind you, always do what you can to awaken the power of your mind.